Okay. Now, so yeah. I have actually said that it will be projects, but you may notice I secretly left it away because I don't believe most of you can handle that. So I will probably give you a special assignment or something like that rather than project. Because ultimately, even if I give you the project in data structure, I realize that there's no project that you cannot find on the internet. Yeah, because data structure is something that whatever topic I give you, you ultimately will find something on the internet. And even the best student cannot, shy away from that because that answer is usually really the optimal answer. So it's like having project for signal and system. Ultimately, I realize that it's a mistake. So we assume that we know projects. Okay, we only have the lab scores. If there are no objections, if you have some objection, I want a project. I will give you a personal project for you. Okay, so it's okay, perfectly okay to send an email to me, and I give you a personal project to work on. But then I have to ask you not to look into the internet because whatever project idea that I think of, okay, on the internet that someone has done it, especially in C, okay. So that's the problem. Okay, I hope that I answered your question. Now, but I will still give you some optional art exercises you see from time to time, which are supposedly harder, and it gives you a hint if you want to try. Okay, what can you go on? Okay, you always see that I give you some optional questions which are more analytical, okay, or empirical in process, to give you a feeling of when people started computer science, okay, what they are thinking about. Okay. Now, of course, now you know that there is an answer out there. Okay, so it doesn't make sense for you to do all the rigorous experiment again just to get the answers that you can click on the internet and get it immediately. Okay. Now, I believe no project is a good thing actually because I think many courses have projects now, so I will skip the project for that. Okay. If you are disappointed, again, as I said, I can give you a personal project. Okay. Now, today we actually go on and talk about something even harder. Okay. Your tutor up on reading the notes have said to me, okay, mentioned to me that we wonder how many students can go on and understand it. But I believe last time in the lab, your tutor said that most of you are actually doing okay. So I'm quite confident. Now, let's talk about the dictionary ADT. Do you still remember what ADT is? Abstract data type. Now, remember when we said we learned about data structure, there's something called abstract data type. Abstract data type is from the user's point of view. Okay, here, recall the definition. An abstract data type is a mathematical abstraction model of a data type. Okay, so it's a complex data type. It is not defined by how it is implemented, okay, because it's abstract. Okay. But by what values it can have, the allowed operations, and what the behavior will be. Okay. So far you have learned only 3 abstract data types: list, stack, and queue. Okay, which are obviously very easy, right? The list is just a list of things. Okay. Stack and queues are kind of a list with very special structures. Okay, queues, you can only join the queue at the very behind, and stack, you can only put new things on the top, and then you can only take things on the top. Now, finally, because we have learned hash table, you can really have some interest in ADT. Now, the ADT we are talking about today is the dictionary. Now, the dictionary, because you already learned about hash table, you already know what the dictionary is. The dictionary is something, an abstract data type in which you have a key, and you always can find some value if it is in the dictionary. Okay? So it is an abstract data type in which help us understand that it's actually the dictionary problems. Now, the dictionary definition, the formal ADT for this kind of problem, as I said, is called dictionary ADT. And if you go online and look for materials, or if you have textbook, it's actually called map ADT. Right? It's also a map from the key to the values. Or in a more strange wording, it's called associative array. Now, why is it called associative array? Because as I said, when I have a dictionary, say I have a dictionary that looks up different people, room number or telephone number. Sorry. So supposing I have a certain dictionary that looks up people's room number. So supposing now I have Tom, and you look up a number SHB 712, and John, and you look up his SHB 617, something like that. Okay, this is some room numbers in CUHK. Now, when you think about it, if you look at the dictionary, you can imagine it is actually also an array, but you do not use index, but rather you use some keys, right? So it's actually kind of an array. Ultimately, you know that there's only fixed number of elements. But it is not indexed, it is associated. Associated means you use some very key from very large universe, okay, to get it. Just like how your brain does it. Your brain associates it, okay? You have a key, you associate something. So actually, it's something called an associated array. Because if you look at a modern implementation, of course your hash table cannot do this, okay? But in modern language, it still looks like an array, okay? So that's why in some modern languages, we call it associative array ADT. Okay? Associative array ADT means I have a key and then I get a value. Now think about it, for an array, the index is a key, right? For every index is a unique, and then you can get a unique value, right? Now not exactly unique value, the unique to your corresponding value. So there's no ambiguity in the array as well. So you see the connection between associated array and array. Now, a dictionary ADT stores key value pairs, okay, and allows the user to find values that correspond to a unique key. Now, the basic operations, every time we have an ADT, we have the basic operations. Now, their names are kind of fixed, okay. So for a stack, remember we call it push and pop, okay. You don't call it insert for some reason, just do it. So for a dictionary, we call it get and put, okay. Now, in a hash table, we do it insert, okay? But in dictionary, we call it get. Get is to retrieve the value of a particular key k, okay? If k have associated to nothing, it should return null, okay? Now, put is that we put a certain key with a value v, okay, into the table. Now, to insert the key value pair of kv into the dictionary, if the dictionary already contains the same key, the value should be updated, okay? So, if I have already that key, I should update that. Okay. Now, here, there are many possible behavior when they attempt to put a duplicate key. Now, in some languages or some libraries, it will throw an error because you say it's unique, right? But in a sense, this is rather strange because, say now I have a table with you, student ID as the key and your score in the course as value. Maybe you do a test appeal, then of course I need to put a new value to your key record. So in most cases, the reasonable is to update the dictionary, okay, rather than throwing an error. But unfortunately, in C# or some other languages, okay, some future language you learn, you actually get an error, okay. So it's kind of strange. Now we can remove a key. Now when you remove a key, you remove the key value pair, okay. You don't need to specify the value. Because with the key, then the value is determined. So when you remove a key, say you drop from this course as a late drop student, then when I remove your student ID, all your record in this course will be eliminated. Now we can have other operations that are very common in ADT, is empty and size, which returns the total size of the dictionary and whether the dictionary is empty. Now we also have some very specific operations. These three operations are keys, values, and entries. Now they return the collection of keys in the dictionary, the collection of values in the dictionary, and collection of all key value pairs in the dictionary. Now these three are very expensive operations in which you export all the keys, or the values, or the key value pairs into a list. Okay, so that's how you connect. Now, but once you export it to a list, then it will be for other purpose. Okay, maybe now you don't need to look up anymore. You want to list out, okay, all students here. So this is operations that are needed. Now, as you can see, if you compare it to say Where so far we actually talk about stack and queue, right? If you compare it with the abstract data type stack, you look at stack, the basic operation is just push, pop, peek, and empty. Okay, it's rather simple, right? If you compare it with dictionary, dictionary is much more complicated. Okay, not to mention that you already know what's behind it. Okay, it's a hash table, and in the lab you realize that a hash table you have the nuisance of finding the good hash function. You have the nuisance of doing propping, right? You have a lot of things. Okay, some of you have said that the propping never stops. Of course, okay? You need to stop it somehow. So here, it is a rather complicated abstract data type. Okay. Now some of you are still confused. I assure you. Why we have an ADT and then we have the hash table? Okay. Now the ADT is an abstraction. The ADT here can be implemented by anything. Okay, I can use an array to do that, right? When you do the lab, you always question, why do I need to do so many things? I just store everything in an array, right? And then I do a search. Now, of course, you know that, okay, when you really have just a few names, then just please use an array, okay? Okay, in a lab, okay, we use examples which are unnaturally small, okay? So that's why you feel like that when you are using hash table, it doesn't make sense, but okay, of course, okay. And ADT will have different implementations, I repeat. We have different implementations when your data type is different. When a dictionary is really small, say you have 10 keys, please just use an array, okay. You can simply use an array to do all these kind of stuff, right? It doesn't violate you. Say you want to put something, you want to check if the key already exists. You just use the search, binary search. Okay, every time you put in, you make sure the order is correct, that everything is still fine, right? When you use an array to implement the ADT, you don't even need to make sure it's unique. You simply go through and put the latest value there. It's completely okay. So ADT is abstract. It's a guarantee to a user, not the actual implementation. Okay. Now, so remember, hash table is only one way to implement a dictionary. Okay, it is favored because it is fast. Okay, it has constant time in lookup, constant time in insert, and constant time in delete most of the time. And be reminded that there is no concept of collision in dictionary ADT. Okay, hash table have collisions. A dictionary have no collisions. So make sure you understand that. When you put the same key into a dictionary, then that is the same key. It could be an update. Okay? There's no concept of hash function in dictionary. It doesn't care. Okay? So that is the difference. So in the future, when you use a dictionary ADT, you don't actually care about the hash function. You cannot specify the hash function. The hash function is the implementation. Okay? So this is something that you have to put in mind, because it says actually some very important concept. Now, so here I say, if we put the same key to the dictionary twice, the value will be overwritten. Okay, this is the same key, and there's no concept of collision. Okay, say we have a dictionary that stores your name against the amount of money in your bank account. Okay, of course, when you put the same key again, I will update the amount of money. Okay? Say you pay your tuition fee, suddenly your bank account is much less money. So in some cases, it can mistake from the user. Okay, say I have a student ID and I get the same score again. Okay, then that can be a score. Okay, so you see the difference between an error in the ADT, okay, and the concept of collision. Collision is your same key hash to the same hash, different keys hash to the same hash, and then you have to handle it. Now in ADT, you don't handle it in the same way. You handle it in a different way. That is the user. Okay, so make sure you understand that. Now, and also, if you look for reference online, you'll notice that people actually made the difference between map ADT and dictionary ADT. Map ADT refers, your textbook will say, map ADT will say that is unique key, unique value. In dictionary ADT, you have the unique key, and then the value can be multiple. Okay. Now that is kind of a outdated, okay, definition. So if you see this definition, you can just imagine it's outdated. You should understand that computer science is a baby stage compared to maths. Right? Maths, we have thousands of years. Computer science, 20, 30, 40 years. Okay. So even for the same term, different people have different meanings. Okay. So here, I would say more than computer science at this moment. Okay. Dictionary is the same as math. And we assume that every key has only one value. Okay? So if you run into any examples that said the dictionary has multiple values, just ignore it. Nobody uses that anymore. Now, say this is an example. Now assume that now I have a name, I have a room number, and I use a dictionary, ADT, to store the data. Now it will look something like that. Okay? Now, originally, if I call is empty, the operation will return true because the dictionary is empty. Then I put Joe 702 is room number in the dictionary. Now the dictionary has the key value pair. Okay, and then now I put Robert 812. Now I put Robert 812, and I have two key value pairs. And I now put Joe 420. Then now 420. Joe will now have updated room number. 420. And now if I try to put N and I put there. And now I try to get William. Okay, there's no William in the hash table. Dictionary. Okay. And then we will see the result will be null. Okay. Now again, you don't see any hash functions here. Okay, it is abstract. Okay, so I don't only know there are certain key value pairs in the dictionary. And the order does not matter. Okay, in the dictionary there's no order. Okay. Now, and if I get Joe, I will get 420. Okay. If I remove Joe, then I will no longer have Joe in the dictionary. If I remove Mary, because there's no Mary, then I get an error. Okay. So that's how a dictionary ADT works. Now, of course, now because I teach hash table first, then you will realize that hash table can do all the things nicely, okay, easily. Okay. So that's why, in most of the time, dictionary are implemented by hash table. Okay. A very lousy conclusion, but you get the idea. Now, to illustrate the difference between ADT and implementation, some of them you still need an example, so I give you an example. Assume now, I have the above example, and I use 3 different ways to implement it. First, a linked list. Second, a hash table with linear probing. Third, a hash table with double hashing. Now, this is what happens. Now, from the user point of view, they are the same. Okay. Say for the linked list, if I input 5 entries, in the linked list is simply a list. Okay. So it's actually a very simple list. So when I want to look up anything, I simply do a search. Here, it's not even, I cannot sort it, right? So I can only do a linear search, okay? And it will be order n. It is okay for 5, okay? And you realize that this is actually okay as an implementation of dictionary. Now, instead, let's use a hash table with linear probing, okay? Now, because we have a name, right? A name is a string, right? So let's use a hash function of that looks like that. We have a hash function. Here we have the string x as the key, and we have Sn-1 times 31 up to the power n-1 plus Sn-2 times 31 up to the power n-2. This is the one that we've seen last time. So each of the character will be converted to the ASCII code and then times a multiple of 31. Okay. If you have been in the lecture last time, this 31 is a mysterious number that people find to be the best. Okay, so we'll be using. Okay, and then ultimately I will get it, and then ultimately I will modulus m, where m is the hash table size. For those who have done the lab exercise, this should not be a problem, right? Ultimately we always have to do the hash table size. Now, as I said, we will try double hashing. So we need a second hashing function to do the collision. Now the second hashing function here is h2. So instead of 31, let's use another prime number, 37. Okay, and then I will do the same hash, but this time I will modulus 7. Okay, so the ultimately largest jump I can do and have double hashing will be 6. Okay, So here I have another hashing function. Now, as a reminder, we have linear probing, right? Go one by one. Quadratic probing, we will try 149. You haven't tried double hashing. Double hashing, we use the original hash value plus I times the second hash value. Okay, so everyone will jump in different steps. Okay, that's how we guarantee that clustering will not occur. So here we have hs plus I times h2s. Again, we need to have a modulus n because we cannot go further than the hash table. Okay, and I will be 1 up to n minus 1. Okay, so yeah, supposedly it is all right here. Now I realize I made a mistake. Actually, the hash2 function, is wrong here. Anyone notice what's wrong with the second hash function here? I actually typed something, mistyped something. What is missing from the hash2 function here? I'm sorry, I need to log in and change the thing. Okay, I give you anyone who can instantly answer.
Power of 2.
Power of 2? No, that's not the problem. There's something wrong, seriously wrong with the function here, hash2 function.
Is it not precise?
What's more
7. Now, it is related to the modulus, but what is it?
Keep 10 or depending on the size of the whole table.
No, there's a fatal error here. Not whether it's good or not. Something is fatal here.
Why is 31 and not 37?
37 is also okay, right? Right? Anyone who discover any
真係睇唔到啊！
fatal issue here, H2S. Now the hint is to look at the double hashing function.
the H2S will give you 0?
Yes, and the second hash function cannot be 0. Right? Because every time I will take a step of H2S, the second hash. If your second hash is 0, then every time you just keep probing yourself. Right? This doesn't happen in linear probing, but look at the formula here. It will I times H2S. So if H2S has a possibility of being 0, then you will constantly be not probing. Okay? So here, usually we cheat. It's modulus 7 plus 1. Okay, I will update the notes. Usually you will make sure that you don't have any 0 value in the hash 2. Okay, so that's something that you need to make sure. If you get a 0, then you just do an infinite loop not infinite loop, but you do n times probing to 0, right? Probing to 0 is useless. And you get the idea, right? Okay, so here, just to make sure that when you do the second hash function, whatever you use, just make sure it never turns out to be 0. Because for double hashing, you will increase by that number every time. Okay, so now I believe the example that I use is actually okay, but I simply made a mistake when I print this out. Now, so as I said, if I use hash table with linear probing, now this will be the result. According to the hash function just now, let's look at the reality. My hash function looks very complicated, but look at it. Ted is 5, Joe is 6, May is 5, N is 5.